Hey everyone, thank you for zooming into my talk. My name is Max Cohen, and I'm currently a second-year PhD student in the robotics lab at BU. This talk is titled Model-Based Reinforcement Learning for Approximate Optimal Control with Temporal Logic Specifications, and this is work I've done with my advisor, Cohen. The motivation for this work stems from the rising levels of autonomy exhibited by complex cyber-physical systems. Specifically, these systems are expected to operate autonomously and complete interesting tasks in increasingly complex environments. The most cited example of this is, of course, self-driving vehicles, but many other examples are beginning to emerge, such as delivery drones and even robots that monitor grocery stores. From a technical standpoint, one could argue that tools from the hybrid systems and formal methods community are perfectly suited to solve the problems posed by modern autonomous systems. These approaches allow one to synthesize controllers for dynamical systems from rich specifications, such as temporal logic formulas, and provide strong guarantees of correctness. The main drawback of these approaches, however, is that they are generally computationally intensive. Another limitation is that formal guarantees in this setting generally rely on an accurate system model, which may be difficult to obtain. On the other end of the spectrum, learning-based control techniques have become increasingly popular due to their ability to solve complex control problems in the face of uncertainty in a computationally efficient manner, yet generally lack formal guarantees of correctness. The main objective of our paper is to bridge the gap between these two approaches by leveraging the strengths of each to benefit each other. Specifically, we'll focus on using learning techniques to improve the computational efficiency of traditional approaches to formal synthesis, as well as allow for the consideration of uncertain system dynamics. Concurrently, we'll leverage tools developed from the hybrid systems literature to provide certificates of correctness for these learning-based control policies. Our overall approach is based on the following idea. We'll pose a sequence of optimal control problems that, if they could be solved, would yield a control policy that satisfies a temporal logic specification. However, solving even one optimal control problem can be computationally demanding, and having to solve a sequence of these problems would become computationally intractable. To address this challenge, we'll take a model-based reinforcement learning approach to approximately solve each problem online, with the added benefit of being able to account for systems with uncertain dynamics. We'll then use a class of hybrid barrier certificates to derive conditions under which this learning-based policy guarantees satisfaction of the specification. Before moving forward, I just wanted to outline the rest of this talk. First, I'll briefly discuss some related works that have inspired our approach. I'll then go into the details of the main problem under consideration. After, I'll talk about our proposed solution to this problem and discuss the conditions required for our learning-based solution to solve the problem at hand. I'll then show simulation results and conclude with a discussion on the limitations of our approach. Before going into the technical details, I wanted to take a minute and recognize some of the works that have inspired our technical approach. This is of course not an exhaustive list, but we'll be drawing on ideas from some of these works throughout the presentation. That brings us to our problem setup. We'll consider the problem of designing a controller for a nonlinear system from a syntactically co-safe LTL specification defined over some finite set of observations O. We assume that the observations of the formula correspond to regions of interest in the state space that can be defined as the zero sublevel set of some function h sub O. Throughout this talk, I'll use the simple example on the right to illustrate some of the key ideas, where we just have some robot that needs to visit two regions without ever colliding with this obstacle. As I mentioned, we'll be considering control specifications in the form of SC-LTL formulas. Importantly, any SC-LTL formula phi can be converted into an equivalent finite state automaton, FSA, that accepts exactly the language of phi. We'll mainly be thinking of this FSA as a discrete system with some finite set of states whose inputs are the observations in the corresponding formula. Given a sequence of inputs, which we'll refer to as a word, we get out a run, which is a sequence of states of the FSA. We say that the word is accepted by the FSA if the corresponding run ends in the set of accepting states. So for our simple problem from before, accepting words would be O1, O2, or O2, and then O1. The main property of the FSA that we'll exploit is this notion of the distance to acceptance, or DTA. We start by defining the distance between any two states in S as the number of transitions required to move from one state to the other. Given any state S, we define the distance to acceptance as the minimum number of transitions required to reach an accepting state. This is essentially a Lyapunov-like function for the FSA in the sense that it is positive definite with respect to the set of accepting states. And the main idea behind our control approach is to force this DTA to decrease along the system trajectory, which can be shown to imply satisfaction of the specification. At a high level, our problem data consists of our specification and system. The first step of our approach is to construct a hybrid system consisting of the formulas FSA and the original system, which I'll refer to as the plant. At the discrete level, the DTA provides us a sequence of regions we need to visit to satisfy the specification. At the continuous level, we use this information to construct a sequence of optimal control problems to steer the system from region to region so as to satisfy the spec. As one of the main results of the paper, we show that the DTA and the value functions of these optimal control problems constitute a hybrid barrier certificate to guarantee satisfaction of the specification. This is again a Lyapunov-like function that ensures we make progress towards satisfaction by requiring the trajectory of the hybrid system to eventually reach a set of accepting states. The main challenges here are that solving the sequence of problems can become computationally intractable and generally requires a rather accurate system model. And so we'll look to learning to address these challenges. The first step to solving this problem is to view the interaction between our continuous plant and discrete FSA as a hybrid system. Here we consider hybrid systems with state Z that can be compactly represented using 4 objects: a flow map, a flow set, a jump map, and a jump set. When Z belongs to the set C, the flow set, it evolves according to the differential equation here, and when it belongs to D, which is the jump set, it changes discretely according to the jump map. For our specific problem, we'll define the hybrid state as the state of the plant, the state of the FSA, and the desired observation. That is, for a given state S, the observation that should appear next in the accepting word. Our flow map is just the continuous dynamics of the plant, whereas the jump map corresponds to the transition function of the FSA. The system flows everywhere outside of the current region of interest and jumps when X reaches the desired region of interest. Going back to our simple example, we see that this just means that observations are added to our word when the system reaches the desired region of interest and a jump occurs. So that's essentially it at the discrete level. So the majority of my focus will be at the continuous level, where for each state of our FSA, we need to find a controller that regulates our system to the jump set while avoiding any bad regions. Given a desired region of interest, we define the regulation error as the difference between the current state and any point on the interior of this region. For any observations that are negated at the current state, we associate a safe set as the complement of these associated regions of interest, which is now the super level set of this function h0, which we assume to be continuously differentiable. So in our simple example here, we just have a system that needs to reach region R01, so we would find a regulation error as just x minus x01, where x01 lies on the interior of R01, and we would define our safe set as the complement of R02. Based on the regulation error and safe set, we then define an optimal control problem to regulate the system to the jump set while remaining in the safe set at all times. To do this, we decompose our control input into a feed-forward term and a feedback term, where the feed-forward term ensures there exists an equilibrium point for the closed-loop system on the interior of the jump set, and we then synthesize this feedback term using optimal control. For notational convenience, we define this coordinate transformation, big phi, to switch between the state and error coordinate system. We then define an auxiliary system, which is defined in the feedback term mu, and encode our reach-avoid objective in the cost function of an optimal control problem. The cost function here consists of 3 terms, encoding that we regulate the system to the desired region with minimum control effort while avoiding unsafe regions. The function b is a barrier-like term that prevents trajectories from leaving the safe set that I'll talk about next. So the barrier term in our cost function is essentially built on top of a control barrier function, or CBF. The nice thing about CBFs is that they tell us that our desired safe set is a controlled invariant set. So the question is, how and why do we encode the invariance conditions given by CBFs into our cost function? For the how part, we recenter the barrier function so that it vanishes at the desired state. The reason for doing this is that CBFs generally do not vanish or necessarily achieve a minimum at our desired state, and we need both of these to ensure our total cost is finite for at least some controls. Performing this transformation retains the high-level properties of CBFs and just introduces the additional property that it is also positive semi-definite. Further motivation for doing this is that we need our value function to be positive definite because we'll be using it as a Lyapunov function to study convergence of the system to this desired region. This also encodes invariance conditions into the HJB equation without necessarily having to study the time derivative of the CBF itself, which will become important when we discuss the situation in which the system model is uncertain. You could show that the optimal policy for this problem guarantees safety provided the solution to the HJB is smooth on the interior of the safe set, which is a strong assumption whose limitations I will discuss later. We also have a simple example here of the effect of recentering the CBF, where we see that it really just pushes the standard CBF given by the orange curve down to 0, which also ensures that the CBF term does not contribute much cost when we're far from the boundary of the safe set. Depending on the specific problem, it may also be useful to scale this function up or down, which controls the conservativeness of the barrier term. One of the main things we show is that the sequence of value functions associated with these optimal control problems, together with the DTA, forms a barrier certificate to establish satisfaction of the specification. The main idea is that the value function decreases along flows and the DTA decreases across jumps. So if we put the two together, we can show that for some sufficiently small lambda, this function VB decreases along the trajectory of the hybrid system, which implies satisfaction of the specification. This lambda term ensures that the decrease of the DTA outweighs the increase in the value function when switching from one optimal control problem to the next. The main limitation of taking this optimal control approach is computation. To synthesize the continuous control policy, we'd have to solve a potentially large number of HJB equations, which would quickly become intractable. This approach would also require a precise system model, which may be unavailable in practice. So, as I mentioned earlier, we'll aim to address these limitations through learning-based control, in which we'll provide a framework to learn the system dynamics and corresponding sequence of HJB equations online. We'll take a model-based reinforcement learning approach to solve this problem, which will consist of two main components: system identification and value function approximation. We'll maintain three approximation structures for learning the system drift dynamics, the value function, and the optimal policy, all of which will be updated simultaneously online. The main idea is, given our approximations, we can obtain a metric related to our approximation error by substituting the approximations into the problem's Hamiltonian and then subtracting away the optimal Hamiltonian, which importantly happens to be 0, and we'll call this quantity the Bellman error. This provides an indirect measurement of the quality of our approximations that we can compute, and our learning objective is then to pick our weights so as to minimize the total Bellman error along the system trajectory. For the system identification procedure, we'll consider the situation in which only the drift is uncertain. Provided this term is sufficiently smooth, it can be represented as some combination of weights and basis functions, plus some function reconstruction error in the case when our basis is incomplete. Given this parametric structure of the drift, we can come up with an approximation by simply replacing the unknown weights theta with some estimated weights theta hat. Now, the traditional approach to coming up with a good estimate would be to record some data points and pose some sort of regression problem. A few challenges with this approach is that we'd have to measure or compute the state derivative, and it may be difficult to ensure the stability of the system if we attempt to do this online. Instead, we'll take an adaptive control approach based on the idea of concurrent learning, which exploits recorded data to perform system identification without relying on the classic persistence of excitation condition. Specifically, we'll use an integral version of this approach to alleviate the need to measure state derivatives. The idea here is that we can obtain an equivalent representation of our dynamics by considering the integral of each term over some finite window of time. Since the uncertain parameters are constant, they can be pulled outside the integral, and the corresponding integrated data can be used for learning without having to measure the state derivative. The main idea is that while our system is running, we'll be saving input-output pairs of data in some history stack, which will be used to update our estimates in real time. Rather than solving this optimization problem, we adaptively update the weights using a recursively squares adaptive update law, whose convergence can be studied using Lyapunov-based tools. The key condition required for these estimates to converge to a neighborhood of the true parameters is for the recorded data to be sufficiently rich, which is formalized by requiring the minimum eigenvalue of the history stack to be strictly positive. And this theme of richness of data will also play a big role in the value function approximation scheme that I'll go over next. In this model-based reinforcement learning approach, the model learned from our system identification procedure will be used to learn the value function of each optimal control problem under consideration. Recall that for each state of our FSA, we're essentially solving a reach-avoid optimal control problem to drive our system into a region of interest without leaving some safe set. The approach we'll take to approximately solve each problem in a computationally efficient manner is to learn the value function only in a neighborhood of the current system state. That is, rather than trying to learn the value function over our entire space, we'll only attempt to learn it within some compact set that follows the system trajectory, which can reduce the data needed to develop a sufficient approximation of the value function. The details of this specific scheme are available in the papers I've cited at the bottom of this slide, but we'll basically be using a linear function approximator where the basis functions are selected as kernel functions whose centers track the system trajectory. Similar to the system identification procedure, we now have some parametric representation of our value function, and the question becomes, how do we get enough data so that our approximation is somewhat representative of the true function? The main challenge that arises here is that we'd like to do this safely, and we'd like to do this completely online, so we really only have one trajectory to extract our learning data from. In this online learning setting, the traditional approach to ensuring convergence of the approximation is to require the system to satisfy a persistence of excitation condition from adaptive control, which can be seen as an exploration type condition. The limitation of requiring this condition is that it cannot be verified for a nonlinear system, and it essentially requires the learning agent to take exploratory actions by including an ad hoc probing signal in the control input. In contrast, the approach we take in this paper is based on the idea of learning the value function via simulation of experience. The key observation originally made in the paper I've cited at the bottom of the slide is that if one has an approximate model of their system, then the Bellman error, which again is our performance metric for learning, can be evaluated anywhere in the approximation domain. So rather than using data only from a single system trajectory, we can simulate the system along various trajectories simultaneously to generate more data for learning. What we'll see is that if these simulated trajectories satisfy some richness of data conditions, then one can ensure the approximated parameters converge to a neighborhood of their true values. Going into more technical details, we can update our approximations using the simulated data through a process known as Bellman error extrapolation. The way this works is that we'll define a family of extrapolated trajectories, x sub I, which are generated by this collection of mappings that map our current state to some other state in our approximation domain at every time step. For example, you could draw these points from a suitable probability distribution at each time step. We can then define the regulation error at each of these points as x sub I minus x sub O, and compute the extrapolated Bellman error by simply evaluating the Bellman error with our current approximations at these extrapolated states. Using this data, we can then change our learning objective from minimizing the Bellman error only along the actual system trajectory to minimizing the Bellman error along both the actual and extrapolated system trajectories. It's important to note that we only update W hat C, which are the value function weights, using this metric, whereas the control policy weights, W hat A, are updated to track WC. Similar to the system identification procedure, we can then update these weights using adaptive update laws commonly used in adaptive control. You can then show that the conditions required for convergence of these weights is for the extrapolated system trajectories to be persistently excited. Again, for a nonlinear system, it's challenging to verify that the PE condition is satisfied. However, the advantage of this approach is that it allows for a virtual system to take exploratory actions rather than the actual system being controlled to generate sufficiently rich data for learning. The question then becomes what sort of guarantees can be placed on the approximations of the drift, the value function, and control policy. We can actually study the convergence of these approximations as well as the stability of the system by using a Lyapunov-like function consisting of the value function weight estimation error, the optimal policy estimation error, and the system ID error. As mentioned before, one can show that if the data collected along the system trajectory is sufficiently rich, then this Lyapunov function decreases to some ultimate bound, where the size of this bound depends on how rich this data is and on the bases used to represent our approximations. Given this result, one can then show that if this bound iota is sufficiently small, then the combination of this Lyapunov function and the DTA from earlier forms a barrier certificate to establish satisfaction of the original specification. So that was a lot of ifs mentioned on the previous slide, and the key takeaway here is that the ability of this learning algorithm to generate a control policy that satisfies the spec is directly related to the data observed along the system trajectory. With all of that, I'd like to take a look at a numerical example to illustrate everything we've just covered. We'll consider a two-dimensional, unstable nonlinear system and a specification that asks the system to visit two regions of interest in any order, and then a third, while always remaining outside of two unsafe regions. We'll assume that the system drift is unknown but has a known structure, so we're only dealing with parametric uncertainty. To solve this problem, we pose a sequence of optimal control problems where we include a recentered barrier function in the cost function for each unsafe region. The resulting value function is then approximated using a basis of 3 polynomial kernel functions, where the centers of these kernel functions are selected to track the system trajectory. On this slide, I have 2 videos of the resulting system trajectory corresponding to the 2 words accepted by the FSA. In each video, the red circles denote the unsafe regions and the system starts in the top left corner. In each situation, the value function of 3 sequential optimal control problems is approximated by extrapolating a virtual system trajectory to one point drawn from a uniform distribution about the current state at each time step. We can see that the system trajectory successfully navigates through the desired regions of interest without ever entering the unsafe regions. I'd like to note that in these simulations, we're using pre-recorded data to learn the system dynamics. However, the approximations themselves are updated online. This slide shows some additional data from these simulations. The bottom left plot shows the system identification error, which decays quickly to 0, and the bottom right plot shows the value function and policy weights. It's important to note that these weights converge to some values that are good enough to solve the problem, but there's no way to know just how good the approximations are, since the solution to the original problem is unknown. So, the key takeaways here are that we established connections between classical optimal control theory and the satisfaction of temporal logic specifications by showing that the DTA and the value function for suitably constructed sequence of optimal control problems form a hybrid barrier certificate. We developed a model-based reinforcement learning framework to solve the resulting sequence of optimal control problems online, and we showed that in this learning-based setting, the correctness of the resulting controller is directly linked to the quality of data observed. Ultimately, the approach outlined here can provide a computationally efficient framework for synthesizing controllers for uncertain nonlinear systems from SC-LTL specifications. Finally, I'd like to discuss some limitations of our approach and ideas for future research directions. The first limitation is that the theoretical results rely on strong assumptions that are challenging to verify. For example, all results are stated under the assumption that each value function is smooth within our safe set, but generally solutions to HJB equations may be non-smooth, and determining conditions under which solutions can be verified as smooth appears challenging. The second limitation is that, in the context of uncertain systems, we assume that we can find a valid CBF for a system without full knowledge of its dynamics. In our approach, safety can be enforced without full model knowledge through learning the value function. However, constructing the cost function in the first place requires knowledge of a valid certificate of safety, which is challenging to check if the system dynamics are not fully known. This brings me to my next point, which is that by taking this approach, safety guarantees are now tied to how well we approximate the value function. To address these limitations, the majority of our work since submitting this paper has been on modifying our approach to make safety guarantees without including the barrier term in the cost function, which has 2 very important consequences. The first is that this greatly weakens the assumption on the smoothness of the value function, since now each optimal control problem is just a standard unconstrained regulation problem. The second is that since the value function no longer encodes safety, we can make safety guarantees regardless of how well learning is progressing. Finally, other interesting directions include extending the approach here to full LTL specifications and specializing our approach to the multi-agent setting. With all of that, thank you very much for coming to my talk. If you have any questions I did not answer, please feel free to reach out to me using the email I have posted on this slide.